8.4, we're testing a claim about a standard deviation or variance. It's going to look familiar because we're pretty much doing the exact same thing. We're doing a hypothesis test. The difference today, though, is when we're talking about standard deviation or variance, it's this chi-squared distribution. And so this one's a little bit different. It's shaped a little bit different. It's not quite symmetrical like we like. And one other thing that's going to come back later is the mean isn't zero. Zero's like over here instead of in the middle. And so that's a little bit weird, and that comes into play later on. We'll see, but we can we can calculate the test statistic using this formula, or of course we can use technology. One thing that's tough about this is if they don't give you the standard deviation of the sample, then you might have to calculate it using another way. Maybe your calculator, maybe your TI, maybe StatDisk, maybe something, I don't know. But you're going to probably need to find that sample standard deviation. All right, requirements say strict requirement, normally distributed population. So we're going to have to test and see if it's normal, and that's fine. We've done that before. The chi-square test does not work well if the population has a distribution that's far from normal. The condition of a normally distributed population is therefore a much stricter requirement. So I just kind of said that when testing claims about the standard deviational variance. We talk about p-value, critical value, and confidence interval methods. This says they're all equivalent for sigma or sigma squared. First example, 1A, p-value method. Below are the heights for simple random sample of female supermodels. Use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than sigma 7.5. So we can think about it more like this. For the population of women, does it appear that the heights of supermodels vary less than heights of women from the population? Now, before we can get into our hypothesis testing, we have to check the requirements. Remember, it's pretty strict about being a normal distribution. And we've done that before on StatDisk. Check it out. I've already got the numbers typed in here. And what we did was we went up to data and normality assessment. Pick column 1 and evaluate. As you recall, we need to look at that histogram on the left over here, and it has to be roughly bell-shaped. Looks good. And then we look over here at the normal quantile plot, and that looks pretty much like a line. That looks good. And then up here at the outliers, looks like 0 outliers. Okay, great. Those three things together are telling me that this is normal. We think this is normal, a normally distributed population. Check. Now we can get into our steps. Step 1 was just give me the symbolic statement, and we're talking about the standard deviation being less than 7.5. Step 2, give me kind of the opposite of that statement, sigma greater than or equal 7.5. We're looking for the equality because that's going to tell me the null. Step 3, we can talk about the null hypothesis. Give me the equal sign. Sigma equals 7.5. There's your null statement. Your alternative hypothesis, give me the one that doesn't have the equals in it. Sigma less than 7.5. This is all the same as what we've been doing. We're just talking about standard deviation this time instead of mean or proportion. Step 4 is the significance level. And they gave that to us somewhere, I think, was 0.01. Step 5, we know we're doing a chi-square distribution. And the reason we know that is from that chart. I mean, when we're doing this, we know we're doing a chi-square distribution. There's nothing to really think about. Is there a question? Step 6 is our test statistic. And we have an equation for that, but you're probably going to rather use technology. But let's go through at least one time with the equation. Chi squared equals n minus 1 times s squared over sigma squared. N minus 1 is the degrees of freedom. And so, that's one less than the number of numbers. There are 16 numbers here. You can count them if you like. So n minus 1, your degrees of freedom is 15. Now S is your standard deviation. Let's see if this is still going to kick on. If you use a TI, you'll have to enter all the numbers in as your L1. Hopefully it stayed on there. Yeah, I've got all those numbers entered in as my L1. You can go stat over to calc and just do one var stats. And that'll give you your standard deviation right there, 1.84391. Or, I don't know if we've done this yet, but if you go to stat disk, you can go to data, and then right here, explore data, descriptive statistics. Gives you a lot of that as well. And you get that same number, that same standard deviation. So again, I think stat disk is maybe easier to use, just easier to type those numbers in, 1.84391. That's S. That's your standard deviation. Your population standard deviation is 7.5. That was the number that they gave us right there. I'm not there yet. I'm not there yet. So we're just doing the chi-square distribution, the test statistic. We type all that in and we get this number, 0.90667. It seems kind of silly, though, to use technology to get this number when we could just use technology to get this number. So if I've got all these typed in, what we're doing, analysis, hypothesis testing, standard deviation 1 sample. I don't know, there's something that I don't, well, let's say you didn't know that standard deviation. We just found it, but let's say we didn't know it. We could just use the data and it's going to find it for us. This one was less than, and the significance level was 0.01. The claimed standard deviation was what? 7.5. That's the number they gave us. And that's from column 1. So we should get that same test statistic right here. I mean, it seems kind of silly to do it by hand and use I don't know. It just, if we've got the technology, why don't we just use it? But 90667, that's our test statistic. But then we go to step 7, and to me, step 7 is the best one because that tells us what we need to know. The p-value. We've already got it pulled up on technology. Let's just go with stat disk. The p-value is 0.0000. Remember the statement, if the P is low, the null must go, right? That's definitely less than our significance level of 0.01. And so that tells me to reject the null statement. When you've got that low p-value, we know to reject that null statement. We're using the p-value method, not the critical value method. So we know we're going to reject. Last thing we do is step 8 is our conclusion. And that's where you probably want to keep going back to this chart. We reject the null. And the claim does not include equality. So this is going to be the language we use for our conclusion. There's sufficient evidence to support the claim that. Again, that chart I think was given in section 8.1. What was our claim? Heights of supermodels vary less than heights of women from the population. Got it? 1B is the same thing. It's just saying let's use the critical value method instead. So let's go back to step 6. Step 6, we found that test statistic of 0.90667. Step 7, instead of doing the p-value, if we want the critical value, if we want to do the critical value method, we've got this right here, 5.22934. 5.22934. And this feels a little bit different than some of the problems we've done this way in the past. We were testing this statement, which tells me that the picture is left-tailed. So let's look at what this looks like. When we draw this picture, it's not symmetrical. Remember, it's kind of hard to draw it not symmetrical. I'm not very good at that. But 0 is not in the middle. The mean is not 0. 0 is actually over here, which makes a difference, because this critical value, if 0 is here, then 0.907 would be here, and 5.22 would be like here. On that axis. So it's just set up a little bit different if 0 is not in the middle, like we've seen in some of them before. So if this is your critical value, then that critical value corresponds with some area right here. That area would be the p-value, whatever we just found in that last thing. But that's the critical region. Our test statistic is in the critical region. And remember what that means is that this is extreme. This is an extreme number. So that tells us to reject the null. It's the same conclusion. Of course, it's the same conclusion. If you look at it from the p-value perspective, this chi-square, this test statistic, has an area, a p-value, that's less than this other p-value or whatever. It's less than, it was 0, so it was less than 0.01. But you can tell it's more extreme than our critical value, so we know to reject. Your conclusion is the same as example 1a. We could write all that down, but we're not going to. There's sufficient evidence to support the claim that the heights of supermodels vary less than the heights of women in the population. Number 2 is the confidence interval method of the same problem. When we do confidence interval from last chapter, we had this equation right here. And so the degrees of freedom is easy enough because n was 16, so we know the degrees of freedom was 15. So that means you've got a 15 right here. And remember, we calculated that standard deviation before. That was 1.84391. But we need the chi-squared right and the chi-squared left values in order to proceed. And so if you think about it, we gotta think about what this picture would look like. That alpha was 0.01, and since we need a left and a right, you can think about this picture. This is 0.01 and this is 0.01, so this must be 0.98 right here. This picture looks like this: chi-squared L, chi-squared R. But still, in order to find those two numbers, usually we can look at a chi-square table. All right, so you can Google search a chi-square table, look like this. Now there's a lot going on here in this table. It talks about degrees of freedom, and we know the degrees of freedom is 15, so we're looking right there at this degrees of freedom is 15, but then you got to figure out which of these numbers to look at. What's important to notice is that it's a right tail probability. Up at the top it says right tail probability, and so you got to think about it as right tail. Like from this number right here to the right of that is 0.99. 98 plus 0.01 is 0.99. But from this number right here to the right of that is only 0.01. So we need to find those numbers in the chart. So we match up our degrees of freedom with the, let's see, where are we at here? Can I mark on this? 15 degrees of freedom. Nope, can't mark on it. And 0.99 would be here. See that number? 5229. And 0.01 would be way over here, this 30.578. So we got those two numbers that we're looking at from that table. chi-squared L was 5.229, and chi-square R was 30.578. Notice it's backwards, though. This is the right number, 30.578, and this was the left number. And that makes sense because the dividing by 30 is going to give you a smaller number than dividing by 5, and you want the one on the left to be the smaller number in this interval. All right, so I'm going to trust you guys to do that on your calculator. You pull that up on your calculator. Square root of 15 times 1.84391 squared over 30.578. I get about 1.29 is less than sigma is less than, when I divide that, I get about 3.12. I'm just curious. Yeah, notice we get that confidence interval right there, 1.29 to 3.12. We can see it in StatDisk, so that's kind of cool, but whatever. We can do it by hand too. We've got that confidence interval. So now we've got to interpret what that means. What does that mean? Well, remember what we were originally wondering was if that sigma was less than 7.5. That was our claim. So the confidence interval here is telling me that we're pretty confident that your sigma is in between 1.29 and 3.12. So if this is telling me that we are, what are we, 98% confident? We're confident that the value is in between 1 and 3. So yeah, we're feeling pretty good about being less than 7.5. So knowing that, this supports sigma being less than 7.5. We're going to reject the null statement. Remember, the null statement was that it was equals, right? We're going to reject that. And so if we reject that, we got the same conclusion. Same conclusion as example 1a and 1b, which was there is sufficient evidence to support the claim that the heights of the supermodels vary less than the heights of women in the population. All right, so for practice, let's do a different one. I wanted to give you one that looks maybe like homework questions. So a simple random sample of 31 men from a normally distributed population results in a standard deviation of 12.1 beats per minute. The normal range of pulse rates of adults typically given as 60 to 100 beats per minute. If the range rule of thumb is applied to the normal range, the result is a standard deviation of 10 beats per minute. Use the sample results with a 0.05 significance level to test the claim that pulse rates of men of standard deviation equal to 10 beats per minute. So kind of out of all of that, that's what jumps out to me. Part A says identify the null and the alternative hypotheses. That's step 3 in our steps. Step 1 was what I just wrote down. Step 2 is give me the opposite of that. Step 3 is the null and the alternative. The null is the one with the equals in it, and the alternative is the other one. Now we want to compute the test statistic. So we can, do we even need to do all of the steps? Step 4, alpha was, what was it? 0.05? Why can't I find it? It says that somewhere, right? Couldn't find it. Step 5, we know that's a chi-square distribution. Okay, fine. Step 6 is our test statistic. So I'm going to do analysis. Oh, we're already on this, right? I'm going to use summary statistics. We want to choose the equals, and the significance 0.05, and the claimed standard deviation was 10. Okay, it's already on 10. The sample size, did you catch that? What was the sample size in this problem? 31, very good. And the sample standard deviation they gave to us was 12.1. So we find the test statistic 43.923. 43.923. Notice they give you the lower and the upper. They give you that x2, or the chi squared L and the chi squared R, but we want this. Test statistic 43.923. C, find the p-value. 0.09693. 09693. 0.09693. If the p is low, the null must go. So notice we're supposed to be less than or equal alpha, which is 0.05. What do we see? It's not, right? 0.09 is not less than 0.05. So what do we do then? Right, very good. Fail to reject the null hypothesis. State the conclusion. We'll go back here. We fail to reject, and the original claim includes equality, right? So this is our language we're going to use. There is not sufficient evidence to warrant rejection of the claim that what are we claiming? The pulse rates of men have standard deviation equal to 10 beats per minute.